In this video, I'm going to go over section 8.5, which is estimating the difference between two population proportions. So it's very similar to 8.4, except that we're going to use a different formula to determine a interval for the confidence interval. So in this example, we have the owner of a popular coffee shop that wants to determine if there is a difference between the proportion of customers who use their own cups when they purchase a coffee beverage and the proportion of customers who use their own cups when they purchase an espresso beverage. Customers using their own cups get a 5% discount, which is displayed on the receipt. The owner randomly selects 50 receipts from all coffee purchases and 50 receipts from all espresso purchases. For coffee purchases, 24 receipts show that a customer used their own cup. So let's write that down. So for coffee, I'll just call it P hat. Coffee is 24 out of 50. And the sample size for coffee was 50. That's what we divided by. So that gives us a statistic of 0.48 for a p hat. For espresso, oops, it's going to change colors. I guess it doesn't want to change colors. Okay, we'll just do bold and blue. So p hat for espresso purchases was 18. So 18 out of 50 gives us 0.36. And the sample size again was also 50. We want to construct a 95% confidence interval for the difference of proportion of customers who use their own cups. Okay, so looking at this, we're going to state that we want a 95% confidence interval for the difference of the proportions of customers who use their own cups. So we want to use p hat of coffee minus p hat for espresso, where so p hat C is the true proportion of coffee drinkers that bring their own cup, and p hat E is the true proportion of espresso drinkers who bring their own cup. So we have to check if it meets the three requirements. The first requirement is it random? So if we're looking at how they selected, she randomly selects 50 receipts. From all coffee purchases and 50 receipts from all espresso purchases. So it says randomly. So that means that it meets this requirement that it is random. We do not have to check the 10% of the population because we are not sampling a finite situation without replacement, but we do still have to check large counts. So what this means is we're looking at, it's not working right. We're looking at the two formulas for coffee and for espresso, where we have to check N times P hat and N times 1 minus P hat. So for, goodness, this is spazzing. Okay, so for coffee, remember P hat was 0.48, our sample size was 50. So we've got 50 times 0.48, which is 24, and then 50 times 1 minus 0.48, which gives us 26. So both of those are greater than or equal to 10, so that meets that requirement. We have to do the same thing with espressos. Remember the p hat for espresso is that 0.36, so 50 times 0.36 is 18, and 50 times 1 minus 0.36 is 32. And again, both of those are greater than or equal to 10, so that means that we've passed the large counts qualification. So that means that we are able to use the formula for the difference in two population parameters. So one thing to note is that when you're doing these problems in this lesson, just like one of the previous ones, it just plugs the values into the formula. You don't have to evaluate anything. So remember that we talked about there are those common values for Z star. So we're looking at a 95% confidence interval. So we're going to use 1.960. They also gave a t-table, that a snip of the t-table that shows other values besides these three. So for some reason they give you something that's different than that, you can use that. I showed it in the last video as well if you needed to write it down or take a picture. But they show it in the previous lesson as well. So all we're doing is plugging into this formula. We're not going to actually simplify. So coffee is going to be 1 and espresso is going to be 2, the way that we set up the problem. So we're just plugging in those p hats, those ends, and that new Z star. So that means that our equation then is, so p hat 1 is 0.48 minus the second p hat is 0.36 plus or minus our critical value Z star is 1.960. And then we're multiplying it by that big square root. So p hat for the first situation, again, was 0.48, 1 minus 0.48 over our sample size was 50 plus 0.36 times 1 minus 0.36 divided by our sample size was 50. Okay, so that's all that it's looking for in this problem. So you're checking which formula has the appropriate values plugged in. We don't have to actually calculate for this lesson. The last thing that we'll discuss on here is confidence intervals and evaluating an argument. Okay, so this example, we have a small town of 5,832 people. The mayor claims that there's a difference in the proportion of voters ages 18 to 30 who would support an increase in food tax and the proportion of voters ages 31 to 40 who would support an increase in the food tax. So they're saying that there's a difference in the younger set of that population and the older in their opinions. And so an assistant to the mayor surveys 85 randomly chosen voters ages 18 to 30 and finds that 62 support the increase. A random sample of 70 voters ages 31 to 40 is surveyed and 56 support the increase. So in theory, we could go through and do exactly what we did in the last problem and find the interval. So we would actually calculate the two values, but they've done it for us on this 99% confidence interval. So they give us a confidence interval of negative 0.25. So that means negative 25% if we think about it that way. And then to positive 10%. So that means the difference is showing that the negative 25% means that the voters 31 to 40 are 25% more likely to support the increase. And then the 10% means that the voters ages 18 to 30 are 10% more likely to support the increase, right? So that's what our confidence interval value, that the value in our confidence interval means. So is there convincing evidence of a difference in the true proportion of voters ages 18 to 30 and ages 31 to 40 who would support an increase in the food tax? So this is very straightforward in terms of how we evaluate. So if the confidence interval contains the number 0 or both positive and negative values. That's how we know that it contains zero, right? If one of them is, if the minimum is negative and the maximum is positive, that interval contains zero, then there is not convincing evidence that the population proportions differ. Okay, so what all that you're looking at is zero a part of this interval? Are they both positive or are they both negative? If they're both positive or both negative, then you would be able to evaluate the situation. Because zero is included, that could mean that there is no difference. Okay, so zero is a plausible explanation. And so that is when you would say that it's not convincing evidence.